Welcome, everyone. Hello. I see a few people I've talked to already at the show, which is great. I'm Christine McMonigal, and with me is Orlando Moreno. We're both from Intel Corporation. We're going to talk today about using Ceph in a hyper-converged infrastructure and some interesting and exciting results we have from that. Do we have the little pointer? Okay, great. Typical legal disclaimer slide. First, I'm going to talk just a little bit about the value proposition with hyper-converged and why it's compelling for use with Ceph as well as just in general. And then we'll talk about a little bit on the background of the project that we were working on, what end user we were working with, and their objectives for this project. And then we'll get into the results and the performance data that Orlando will be able to share. All right, hyper-converged. So just to level set, what do we mean by hyper-converged? What we mean is that you're able to run compute workloads and applications on the same servers that are running your storage workloads and managing your storage services. So this is a virtualized environment, and all of the servers that are running this are clustered together into a virtual pool of compute and storage resources over a standard Ethernet network. The data then is distributed across all the different nodes in the cluster, whether it's the application or the storage data, distributed across that cluster. And then the rest of this is very similar to what you'd probably already be familiar with for Ceph. The design is very flexible. You can incrementally add server nodes as needed, and each time you add a server node to your cluster, you're adding those compute and those storage resources. So it scales out in a very effective manner. And one of the most appealing things about hyper-converged is that it can be deployed and managed using virtualization tools that a lot of people are already familiar with. So it doesn't take a specialized skill set. Hyper-converged is becoming one of the most predominant architectures used for private and hybrid clouds in the enterprise. Let's look at a little bit of data here. This is the latest from IDC that was just released a couple weeks ago, actually. And you can see here that the market's been growing rapidly for hyper-converged. It's grown 64% just in the last year. And IDC categorizes this as part of the larger converged infrastructure market, and it's grown at 6.8 times the overall converged infrastructure market. Oop, I jumped ahead here. Yeah, so this is some research from TBR on why people are using hyper-converged. And this data showed that about half the companies they surveyed already were using it, and another quarter had it in evaluation. We're planning to adopt it in the next 6 months. And some of the key reasons are on the far right there. Infrastructure costs, it's a very cost-effective way because of the efficient use of compute and storage running together on the same servers, but also an efficient use of people resources if you can have the same tools and the same methods that you're managing your VMs used for your storage as well. And that makes it particularly suitable for specific lines of business or specific workload needs where they may need something very quick and easy to deploy. A little bit more from TBR here. On the left side, this is showing whether people are using it for standard infrastructure or for a private cloud or both. So the blue there shows the people using it for private cloud, and then the kind of peachy color there is people using it for just traditional non-cloud architectures. And then the green is people using it for both. And so you can see that that's really a predominant method the larger the company. And then on the right side is the top workloads that people are using hyper-converged for. Databases, cloud hosting being the top two. Okay. So that's what hyper-converged is. Let's talk a little bit more about the specific project that we've been doing. So we've been working with a customer that's a large telco, And we set out to help them prove out that you could run Ceph in a hyper-converged infrastructure on OpenStack. They needed the infrastructure to be able to support multiple tenants that were running a wide range of workloads, top of which were virtualized network functions, databases including transaction processing, and a virtual content distribution network. But there were more workloads beyond this, and you'll see when we go through the data that this could be suitable for a wide range of workloads, compute and storage. We focused here on using Ceph for block storage, but of course Ceph supports object as well, so you could do something similar for that. And then the goals of the partner that, or end user that we were working with, this large telco, was that they really wanted to understand what would the behavior be of the system, how would it utilize the CPU and the memory and balance those resources, and how would adding compute functions onto their storage cluster stress out that underlying storage subsystem. So that's what we set out to prove with them. And of course, because we're Intel, we wanted to make sure that the clusters were using our latest generation Xeon scalable processors that we launched last year. And we also used our Intel SSDs in the cluster as well. We didn't have Optane drives available at the time. That's in the picture there, the black card there. But if we were to start this testing again today, we would definitely add Optane into the cluster as well. We've done other testing that proves out that using even just one Optane drive to do the metadata or journaling in Ceph can provide a dramatic reduction in latency. And if anybody wants to see more on that, we've got a demo running downstairs in the Intel booth where we have some really good data showing the impact with and without Optane for metadata. So we would recommend adding that, but at the time what we had available was the 3D NAND SSDs. All right, I'm gonna hand it off to Orlando now, who can start sharing some of the actual data.
Yep, thanks a lot, Christine. So like Christine said, we sought out to provide our telco customer with some sort of hyper-converged Ceph cluster with OpenStack. So we used a 10-node Ceph cluster that also ran OpenStack Nova, and each node had 4 NVMe drives. It's a 3x replicated pool, and for the time being, we only ran 1 OSD process per NVMe. The version of OpenStack was, at the time, Mitaka, and then Ceph Joule file store was what we used. So each node was the latest Intel Xeon Platinum 8176 processor. The memory for each node was provisioned pretty high because of the requirements for memory usage for each node. And then the network was 100 gig total, but we used 4 25 gig network interfaces to create both the cluster network and the public network, which is all shared, and you can see at the top there. Across the 10 nodes, we used 3 different monitors co-located onto those nodes. Just for availability, the recommendation is usually 3 monitors, but as a separate system, we used an OpenStack controller just so we can manage all the different services. So in terms of performance testing, we have a little bit of a test plan that we set out to complete, which is using a simple benchmark, which is FIO, to run on each of the VMs that access the Cinder volume. And then we run a couple different workloads like reads, writes, and then a mixture of them. And then each VM is sized according to our telco customers' needs. So 4 virtual CPUs, 2 gigabytes of RAM. The attached volume was roughly 32 gigabytes in size. And then what we would like to see is how many VMs can we scale amongst this 10-node cluster. So we ran 5 to 50 per host, so a total of up to 500 VMs total. So as we ran these workloads, we scale the I/O depth, so kind of simulating an increase in client traffic. More concurrent I/Os going to the cluster also means more IOPS that the cluster provides aggregate. But one thing that we've noticed is as you increase the VM density for each node, the VMs struggle to provide higher IOPS at high Q depths. So per VM, it ranges from 1,000 to 20,000 IOPS, but this can all be changed if you place a IOPS cap or some kind of quota, which most service providers do use. That keeps a single VM from using up all the available resources or IOPS that the cluster can provide. So as you can see on the x-axis, we increase the I/O depth of the workload, and then on the y-axis is the total aggregate IOPS, and then each line represents the total number of VMs that were running this workload. So the previous slide was for random reads. A 4K random write workload is more interesting because Ceph does 3x replication, which makes writes pretty expensive. And as you can see, the amount of IOPS that a VM can provide starts to diminish as you increase the I/O depth as well as the VM density. So per VM, we reach roughly 200 to 1,500 IOPS per VM. And again, if you were to constrain or put some quotas on this, you could probably increase your VM densities and provide a certain level of IOPS. The mixed workload is something a lot of customers are interested in, just because it's not always random reads or 100% random writes. It's usually a mix, either 70-30 or 50-50. So the thing to point out here, though, is that because Ceph, the write operations are so expensive and it causes the performance to be dictated by the writes, you can see the mixed workload looks a lot like our write performance. So if you size your Ceph clusters to be expecting write-heavy workloads, then your mixed performance is going to roughly follow the same pattern. So during our testing here, we actually upgraded our cluster from Joule to Luminous, just because as we were recreating cluster for different tests, Ceph Ansible decided to upgrade. So we decided to look at what the performance difference was, and hopefully it's an increase. So we reran the same test. It's still file store, but we like to see what is the impact of moving up to this new version. So taking the two corner cases, random reads and random writes, trying to scale the VMs. This time I just chose one QDEP, which is 8, and then one specific use case, which is one num job. And as you can see, the performance across the board in terms of scalability is a lot better in Luminous compared to Joule. Now, there's a couple of interesting things that we saw as we upgraded our cluster to Luminous, is that as we got more read IOPS, we also used up more CPU, which is something we kind of focused on in this experiment, is because the CPU is also being shared with Nova, or the OpenStack services. So yeah, we're getting more IOPS, but we're also utilizing the CPU more. The good thing, though, for at least the random write case, is that we're seeing lower CPU for our write operations, which we can hope to say it attributes to some of the performance optimizations made in the Luminous release. And then this is also important because with lower CPU due to the storage, we can use more CPU for our applications, such as the OpenStack services. So speaking of CPU and system resources, I want to talk about how do we control the storage and compute resources, and how do you manage all of that within a cluster. So again, it's important to balance those two budgets, storage and compute, in a hyper-converged architecture. Specifically from our telco use case, the storage budget was set at 20%. So for each storage node, whatever storage you decide to use, in this case it's Ceph, it can only use up 20% of the node's CPU usage. And of course, this puts some sort of resource constraint on our cluster, and it will affect your performance that the storage cluster can provide. So there's a couple things that you can do both on the storage side and the compute side. In terms of deployment and production purposes, you do want to modify your Nova configuration or whatever your compute nodes are to be aware that, hey, you're also sharing resources with Ceph. So one way you can control Ceph is using C groups and systemd. You can put a quota on the CPU for Ceph processes. In this case, we decided to put a 20% CPU quota on our Ceph OSD processes. As you can see, we can change the workload, and the green line represents the Ceph OSD CPU utilization. Ideally, we want it to just stay at 20%, so it gives us more room for our applications to use up that rest of that CPU. Now, of course, it doesn't go up to 100%, but for the Nova instances, but this is kind of showcasing that you can keep Ceph under control in terms of CPU usage. So what does having a quota do to your IOPS, and also how does that affect your different quotas? So what we did on the x-axis here is we changed that quota from 20% to 15% to just having no quota at all, and being able to constrain your Ceph CPU usage also changes the behavior of your different workloads. So you have your 4K random reads and your 4K random writes, again, these corner cases. And as you add more constraint to your Ceph OSD processes, you also kind of restrain the IOPS that they provide. So the Ceph CPU usage in general maxes out between 25 and 50%. So between the 25 and 50% CPU quota is where Ceph use is pretty much bottlenecked. And enforcing a 20% CPU quota causes roughly 30% impact on your IOPS. And as we were doing these experiments, we tried looking at, okay, what can we do to help reduce those performance impacts from enforcing a quota? One of the things is to kind of affinitize your CPU cores so that they're local to your Ceph OSD processes. So again, we use systemd to do this, and there's a control option called CPU affinity, where you can specify the CPU cores that run the certain service, and in this case, it's the Ceph OSD service. So this is just an example. If you set CPU affinity equal to all of these cores here, which all belong to socket 1, this assumes that the Ceph OSD is running on devices that are on socket 1, or at least that the NIC is on socket 1. So doing this is actually important because the idea is that if they run on the local NUMA node or socket, you don't have to remote access the memory, or the cores that are running all get memory from the local NUMA node. Now, in terms of what that means for performance, the effect that we saw was random read performance increases by about 16%. For writes, it didn't show much improvement, but this is again something where we have to kind of tune and optimize for various different workloads. So the graph here shows having a CPU quota at 20%, as well as affinitizing your cores to the Ceph OSD nodes, or Ceph OSD processes, sorry. And again, in terms of scalability, we try to show more VMs, and does that affect the performance? So across the board, you're getting about 15 to 16% more IOPS when you affinitize the cores to your Ceph OSDs. So in terms of hyper-converged architecture, we like to see, okay, how does it scale if we add more storage devices? In terms of capacity, these nodes were equipped with 4 terabyte drives, NVMe drives, and 4 per node. So there's 2 ways you can kind of scale the storage and the performance. Is one, add more NVMe devices to your nodes, And then for performance, add more OSD processes to each NVMe drive. Now, the general practice is to just put one OSD process on your NVMe drive. But in our case, we decided to put more to see how much performance we can get. Now, there's a trade-off for doing this, and that includes CPU utilization increasing because more OSD processes are running on the same host, as well as your failure domain. So if an NVMe drive goes down, whatever many OSDs were located on that NVMe drive also go down. So you kind of have to take into account how to balance that number. So this here is showing two different ways that we scaled our storage. One is adding 4 more NVMe drives per node. So we went from 4 NVMe drives per node to 8. And then the other is to add 2 OSDs per NVMe drive instead of 1. So as you can see, you have 4 NVMe per node, and then adding 2 processes to that, and then 8 NVMe's per node, and then adding 2 processes on that, for a total of 16 OSDs at that last case. Now, what we showed is just one use case for random writes, but the general performance results is that as you add more NVMe drives, you get more performance. So for the random write case, it's about a 44% increase in IOPS. Also, co-locating more OSDs processes onto the NVMe drives also pulls more performance. But again, that also means your CPU utilization increases. So in a hyper-converged infrastructure case, you want to be careful of doing this if you do have some sort of CPU quota. So in summary, we talked about the hyper-converged infrastructure, what are its benefits, such as lower footprint, lower cost of entry, being able to utilize your hardware more efficiently. The cluster that we showed utilized our latest Intel NVMe drives as well as our latest Intel processors. And then we showed some performance improvements due to the Luminous release, as well as what you can do to control your compute and storage resources. All of this being done with standard Linux tools, and of course there's a lot more work to be done to optimize Ceph as a solution for hyper-converged infrastructures. Well, thanks a lot, guys, for coming by.
All right, thanks for coming.